My name is Reagan Cox, and this is my presentation for Lab 1. So in this lab, we used clear tape to demonstrate the amount of excess charge present in an ordinary object. So in order to do this, we used Newton's second and third law along with Coulomb's law. Newton's second law allows us to use gravity to calculate the force on each tape. Newton's third law dictates that the force on the top tape by the bottom tape was equal to the force on the bottom tape by the top tape. Additionally, Coulomb's law helps us to calculate the vector electric field of a charged object, which in this case was the charged tapes. At the end of the experiment, I calculated the charge of the tape to be 8.35 times 10 to the negative 9th coulombs and 5.22 times 10 to the 10th excess electrons. Several assumptions were made throughout this experiment. We assumed that the tape acted as a point charge with all the charge located in the center, and we ignored air resistance. Assuming that the tapes were point charges with the same magnitude allows us to use Coulomb's law to calculate the charge, and ignoring air resistance allows us to set the gravitational force and the electric force equal to one another. To perform the experiment, the tapes needed to be negatively charged. As shown to the right, the tapes were placed on top of one another and quickly removed. This was done for both tapes to make sure that they were both negatively charged. Once the tapes were charged, one piece was placed across two textbooks and the other piece was placed underneath. The tape on the bottom caused the tape on the top to float, and the distance between the two tapes was measured. Because both tapes repelled when placed next to each other, we can conclude that they have like charges. When placed near a positively charged pen, the tapes experience an attractive force indicating that both tapes were negatively charged. This repelling force between the tapes was observed when the top tape began to float, indicating that the electric force from the bottom tape was counteracting the gravitational force on the top tape. Using the measured length and width of the tape and its surface area, we're able to calculate the total number of atoms present by dividing the surface area by the size of an atom. So my observed vertical distance was 0.19 meters. So because the gravitational force on the tape was equal to the electric force, we can use Coulomb's law to solve for Q, the charge of the tape. So to find the number of excess electrons present, the charge on the tape was then divided by the charge of a singular electron. So the resulting ratio of atoms to electrons was 7.8 times 10 to the 6 atoms for every 1 electron, and the calculated charge was 8.35 times 10 to the negative 9th coulombs. Moving on to the coding section of the lab, I first treated the tape as a point charge, so I used the measured quantities and Coulomb's law to calculate the charge, which ended up being 8.3 times 10 to the negative 9th. As shown in the visual, the electric and gravitational force on the top tape are equal in magnitude but opposite in direction. Next, the tape was treated as a line charge. I created two line charges that were placed. They measured vertical distance away from one another, and then I iterated through the top and bottom tapes to create a visual for the electric field. So the green arrows show the electric force from the bottom tape to the top tape. The white shows the electric force vector, and the yellow shows the gravitational force vector. Moving on to the conclusion questions, if protons were negative and electrons were positive, the direction of the tape's electric fields would flip. The signs for all the calculations would also flip, but because the magnitude of the charges is unchanged, the tapes would ultimately behave the same. When the tape was treated as a point charge, I calculated a Q value of 8.3 times 10 to the negative 9th, but when it was treated as a line charge, I calculated a Q value of 8.3 times 10 to the negative 10th. Because we assumed that all the charge was concentrated at the center of the tape in the point charge model, the calculated Q value was much larger. The line charge model is definitely more accurate because in reality, the charge would be spread equally over the entire piece of tape. In conclusion, this lab demonstrates how we can use physics principles to calculate the charge and excess electrons on ordinary objects. This lab demonstrated how like charges, like the tapes, repel while opposite charges attract. However, because several assumptions were made and human error is impossible to avoid, the calculated results should vary slightly from the actual charge and number of electrons on the tape.